Hey there. So to continue our study of phase transformations, I want to talk about kinetics, which is the study of the reaction rates of the phase transformation. So what they do, first of all, to determine those reaction rates is they measure the degree or fraction or percentage of transformation as a function of time while they hold the temperature constant. Now, how might they do that? Well, you could put your sample inside of an X-ray diffraction machine, X-ray diffractometer, and then continuously take diffraction patterns as time goes on. And remember that crystalline structures have changes in the diffraction pattern based on the crystalline spacing. So that's one way to do it. Or you could measure another property of the material that changes as the phase transformation takes place. For example, electrical conductivity changes as a material goes from a liquid to a solid. And so does the speed of sound. Remember that the speed of sound is actually higher for solid materials than liquid materials. So you could measure one of those properties as the transformation takes place and map its progress over time. So there's a couple of different ways to do it. But regardless of how you do it, you can generate these plots that are, I think I'm saying this right, Avrami plots. So in the Avrami equation here, it's shown here as y equals 1 minus e to the minus kt to the nth power. Here y is the fraction transformed, the percent, for example, that's transformed over time. T is the time, and then k and n are transformation-specific parameters that depend upon the material, what phase transformation it's going through, and other factors. So they're basically fit constants. So you generate plots that look like this. Now, in this, of course, you start off here at 0% transformed, where it's still a liquid, and then as time goes on, it's going to follow that exponential function and increase until it reaches 100% or fraction 1, and then the transformation is considered complete. Now, by convention, the transformation rate is cited as 1 over the time that it takes for the reaction to be completed halfway, or 1 over the half-life, I guess, kind of similar to radioactivity there, of the phase transformation. Now you can look at these Avrami plots for different values of supercooling, different values of delta T. So here we see decreasing values of delta T, and you can see that as you supercool the material less, as you cool it 135 degrees, for example, below the melting temperature, all the way down to simply 43 degrees below the melting transition temperature, as you do that, the time that it takes for the material to form a solid increases by a lot. And this is, of course, a logarithmic scale. So sometimes those rates are often so slow for just a small amount of supercooling that the attainment of an equilibrium state isn't possible. Now, what happens is, let's say, for example, that we're looking at an iron-carbon system. We talked about the phase diagram for the iron-carbon system in the last chapter, chapter 9. So here it is again, to refresh your memory. There's the phases. Remember that as you increase the percentage of carbon by weight percent, you get this intermetallic compound, which is known as cementite. We have our austenite phase, and we have our alpha ferrite phase, and then you can have a mix of phases here. So that's all present on this system. Now, when you go at this this transformation right here, this is a eutectoid isotherm that happens at 727 degrees Celsius. Okay, so that's the eutectoid line right there, and it's called that because you go from the gamma phase when you're at this eutectoid concentration, which is 0.76% by weight carbon. You go into the from the gamma phase to the alpha or ferrite phase plus cementite. Okay. And then the structure that's formed as you go across this at the eutectoid concentration is known as pearlite. When you go from austenite down across that eutectoid, you go into the region for pearlite. Okay, now for this transformation to occur, you have to cool the material below 727 degrees C. So you have to undercool it or supercool it. What happens as you do that is, to form the pearlite, is that you get these lamellae of the cementite and the alpha phase in regions. Usually this starts at a grain boundary, okay? It starts at a grain boundary and it grows outward into perlite from austenite, okay? And that happens by diffusion. So you have the diffusion mostly of carbon. It diffuses faster and the carbon moves around. The cementite has a higher concentration of carbon, and so it moves to the cementite phase right there. Now, they call it coarse perlite when the lamellae are thicker layers, okay? And that happens at higher temperatures. And you have thicker layers at higher temperatures because you have more time for the diffusion to occur. The diffusion occurs faster at higher temperatures, and because the diffusion occurs faster, then you can get those thicker layers happening. So they call thick lamellae coarse perlite, and they call fine perlite very thin layers of the alpha phase in the cementite, okay? So if you look at this, you might think that you would have to generate these Avrami plots for a lot of different things. Remember that those Avrami plots were generated by quenching the material to a specific temperature and then holding it at that temperature to completion of the phase diagram. So that actually, what you'd have to do is, let's say you know in your factory you want to quench to 550 degrees Celsius and wait. Well, you'd have to find an Avrami plot for quenching to 550 degrees Celsius and waiting. And that would be different from the Avrami plot for 600 degrees Celsius, and it would be different from 625, and so on and so forth. It would also be different for every different possible concentration of carbon that you might have. So that's a lot of Avrami plots, and it's a lot of things to look at. So what they do instead is they generate these things called isothermal transformation diagrams. So what it is, it's sort of a summation, if you will, of a lot of Avrami plots. So it still only has one concentration of carbon in it. So 0.5 weight percent by carbon, for example, might be your plot, okay? But it sums up all the Avrami plots from the different temperatures. It generates it then like this. Let's say that this is your Avrami plot for 675 degrees Celsius for this phase transformation to occur, okay? So it takes the onset of the phase transformation and compares it to the completion of the phase transformation and then the halfway point. Okay, so those become, for the onset, the green curve here, okay, and for the finishing, the red, and then for the middle, the dashed line, okay? But it compiles those for a whole bunch of different temperatures, okay? So you can see that as you supercool the material, as you cool it to a larger delta T, then what happens is the crystallization process happens faster. And so here's a logarithmic scale of time here on the bottom axis. So here you have 1 second, 10 seconds, 100 seconds, 1,000 seconds. Well, if you're at 675 degrees C, it takes, say, I don't know, what is that, 50 seconds or so for the reaction to begin. But if you're down here at 550 C, it only takes 1 second for that reaction to begin. If you're here at 675, it takes maybe 500 seconds or so for that reaction to complete, okay? But if you're down here at 550 degrees C, it happens in less than 10 seconds. So you can see you can extract that information about how long it takes these reactions to occur as a degree of the temperature that you cool it below the eutectoid temperature. And the eutectoid temperature is indicated on here for this horizontal brown line looking here, okay? It indicates the eutectoid by showing that above that line, above that temperature, you just have austenite, and that's stable. And then as you go below, what you have is on the left of the green curve, you've got austenite, and then on the right of the red curve, you're 100% transformed into perlite. Okay, so as you move to the right, you're going through that phase transformation. Okay? Okay, so that was for the eutectoid composition. All right, so this is the eutectoid composition, which is 0.76% by weight of carbon. All right, so what you do is on your isothermal transformation diagram, if you want to figure out exactly what you've got, then you draw lines to indicate what you're doing to the material. So for example here in black, it shows that you're beginning at a temperature of 727 degrees C at higher than your eutectoid, so that's up here, and then you rapidly cool it to 625 degrees C. So that's shown here by that black kind of diagonal line that goes from above the eutectoid down to about 625. So that's rapid. It happens in less than a second. And then it says here, you're holding the temperature constant at that value, and you want to see what's happening to the material, okay? So holding the temperature constant, that's a horizontal line that you draw across, and then what you can see is what happens to the material as time goes on. And so the reaction goes from austenite, and then the onset to perlite happens at maybe a couple of seconds. It's 50% completed at, say, 8 seconds, and then it's 100% completed at, say, I don't know, 15, 20 seconds here, okay? So that's what's happening reading off. So this is what you actually physically do to the material here on the black line, sort of superimposed on this isothermal transformation diagram. Now that's for eutectoid compositions. If you have non-eutectoid compositions, then what happens is you get the formation of those pro-eutectoid particles. So if your composition is less than 0.76% by weight, then those pro-eutectoid particles are ferrite particles. And if they're greater than the eutectoid composition, then you get cementite particles forming. Okay, so here in this transformation diagram, the concentration of carbon is 1.13% by weight carbon. So you can see here that the formation of those pro-eutectoid cementite particles happens above the eutectoid transformation temperature. Remember our phase transform plots from chapter 9, here is our 1.13% by weight line, so that shows the concentration, and then you can see that above your eutectoid 727, what you've got is a mix of two phases, and that is your gamma phase and your cementite. So you've got these pro-eutectoid cementite particles forming. That's indicated here on your isothermal transformation diagram with this blue curve, okay? So to the left of the blue curve, you've got all austenite, and then once you cross that blue curve, you've got some cementite particles mixed in. And then if you're below your eutectoid, the stuff that was austenite is going to slowly move over and become that perlite as time goes on, and that's indicated here with the green and the red lines here. All right, so that's how you do that. Now, if you supercool, in addition to the stuff that was shown on the chapter 9 diagrams, the austenite, the perlite, the pro-eutectoid cementite, and ferrite particles, in addition to those equilibrium structure particles, if you supercool, if you have a very large delta T, then you can get non-equilibrium structures, and they don't appear on that standard iron-carbon phase diagram that we learned about in the previous chapter. And they don't appear because the solidification occurs too fast for those equilibrium structures to form, and so you get these non-equilibrium structures. Now, if you give it enough time, maybe the age of the universe or whatever, then it would move out of those non-equilibrium structures into something that would appear on your phase transformation diagram. Okay, so the first of those that I'd like to talk about is bainite, which is, of course, another transformation product that's a non-equilibrium structure. Bainite is defined as these elongated needle-like cementite particles within an alpha ferrite matrix, okay? So instead of forming these lamellae, these structures with these layers in it, what happens is instead of that, you get needles of cementite that form. In other words, the diffusion hasn't had time to progress, and so the cementite starts to clump together, but then it just kind of freezes in place because the transformation happens too fast. Okay, now this is indicated on these isothermal transformation diagrams by this dashed line. Okay, below a certain amount of supercooling, you're just not going to get that perlite forming anymore, okay, and that's indicated by this dashed line here. And below that dashed line, instead of going from austenite to perlite, you're going from austenite to bainite, okay, as you move to the right. So it's just too supercooled, it happens too rapidly, and then you're going to get this these non-equilibrium structures forming. Another one is spheroidite. And in this one, what happens is that your cementite particles are sort of spherical, hence the name spheroidite. within your ferrite matrix. And this requires diffusion. So what you do to get this non-equilibrium structure is you take your bainite or your perlite and you hold it at a temperature just below your eutectoid for a long time. Say it's 715 degrees Celsius or something. So you hold it there and you let that diffusion process occur for a long time. And what happens is the driving force for this is that the best formula or the best shape for a surface tension, what lowers the surface tension the most is, of course, a sphere. And so after a while with diffusion, if you allow it to just sit there and diffuse for a long time, but don't take it back through the eutectoid so that it's transforming back into austenite, right, then your cementite will move until it's forming these little spherical structures, okay? And so that's spheroidite. Another non-equilibrium transformation product is martensite. And this is when you supercool it so much that it just doesn't have time to make that phase transformation away from the austenite. And so what you get is you get austenite with these sort of structures in there with needles of martensite. So you have sort of an austenite matrix with needles of martensite. And what martensite is a BCT, a body-centered tetragonal structure with the carbon moving into some of these potential sites here. Okay, so that's where the carbon likes to sit. Okay, now martensite is a lot more brittle than what you would find for any of the values for perlite or for ferrite, any of those things. It's a lot more brittle. It's a single phase, and it's sort of a diffusionless transformation because the needles are taking place and they're not forming these sort of phase segregated regions. There's very few slip planes for this stuff. It's basically frozen in place, and that makes it really, really super hard and brittle. So hard and brittle that it's almost useless. Now, if you look back at this, it's really all about the amount of supercooling that you apply. So if you only cool it to, say, maybe 200 up to 200 or so degrees below that eutectoid transformation, then you can get your stuff to transform into perlite. If you cool it more than that, then you get bainite. And if you cool it even more than that, maybe 500 degrees below your eutectoid, then you're going to get martensite. Okay, so let's take some of the stuff that we've learned about isothermal transformation diagrams and apply it to an example. So using the isothermal transformation diagram, specify the nature of the final microstructure, what's present at what rough percentage, that's been subjected to these heat treatments. So you take your material, you cool it to 700 C, you hold that for 10 to the 4th seconds, and then you quench to room temperature. That's the first one. The second one, cool rapidly to 400 C, hold it for 2 seconds, and then quench that to room temperature. And then finally, cool rapidly to 400 C, hold it for 20 seconds, and then quench that. Okay, so let's go through, and I'm going to draw what's happening for each of these processes on my isothermal transformation diagram. So the first one I've shown here in black. I'm taking it, I'm cooling it rapidly to 700 C. That's indicated by this near vertical line right here. And then I hold it for 10 to the 4th seconds. So holding it at 10 to the 4th seconds at the same temperature at 700 C, that's a horizontal line that stretches from the end of my first line all the way out to here, which is 10 to the 4th. All right? And then I quench that to room temperature, and that is a near vertical line quenching down below my 100 degrees line here. Okay, so what have I got? Well, if I go across here, you can see I'm holding it for a long time. My horizontal line crosses the onset of the transformation right there, and it doesn't make it to the other side. So I think it looks like about 50% of the way transformed, I guess. And then I quench, okay? So if it's only 50% transformed when I quench, then the rest of it will become martensite. So I'm going to say that I got 50% coarse perlite and then 15% martensite for that material. Next one, I've indicated this one in red. Cool rapidly to 400 C. That's this near vertical line all the way down to 400 C. hold for 2 seconds, that's my little horizontal line right here that only goes out to 2 seconds or so, and then quench to room temperature, another near vertical line. So you can see that what I've got here is that it's really not even had time to transform to bainite. You can see that I've cooled it so much that it goes below this perlite to bainite transformation here. So it would be bainite if I let it alone for a while, but I'm not letting it alone. I'm quenching it again. So this brown line right here corresponds to the onset of the transformation to bainite, but it doesn't hit that. So that means that I've got 100% martensite for that material. And then finally, cool rapidly to 400 C, hold for 20 seconds, and quench. Okay, so this one I've indicated in blue. Here's my near vertical line for cooling rapidly, okay? And then I cool it to 400 C, and then I hold that for 20 seconds. I'm indicating that with this blue horizontal line, okay? So you can see that if I hold it for 20 seconds, it goes into this region where it's transforming into bainite, but it doesn't quite reach the 50% line, so I'm going to estimate that at 40% or so. It's just an estimate. And then I quench, and the rest is going to become martensite. So I've got 40% bainite and 60% martensite for that material. Now, if I add in, so that was just for plain old carbon mixed in with iron. If I add in other things, like I'm making a steel, for example, and I have other dopants like chromium, nickel, moly, silicon, manganese, whatever else, then that's going to change my phase transformation diagram. It's going to change my isothermal transformation diagram as well. And what it can do is it can change the transition temperature. So you can see that the on-site for becoming martensite down here is shifted upward, so that changes the onset temperature. It can also change what's called the nose. The nose it refers to as the bump kind of in the isothermal diagram, so it can change the nose to longer times, okay, so it kind of moves it over, makes it take longer to form perlite. And it can also add another nose in the bainite region. So here it kind of goes out and then in and then out again, so that's adding another nose for bainite, okay? So it can do all of those things to the transformation diagrams. Now, I drew a whole bunch of straight lines in the previous example because we were quenching and then holding and then quenching, right? But that's actually not too, practical for a lot of factories. What happens instead is that, let's say they take it out of the furnace and then they just let it sit there in a room that has a temperature of whatever, and then it's going to slowly cool. Your material is going to slowly cool from the austenite, for example, to the other material. It's going to slowly drop in temperature. So if you do that, then you have instead a continuous cooling transformation diagram. The lines that you draw on the curve won't look like abrupt vertical and horizontal lines so much as they'll look like arcs, like are shown here on these cooling curve in blue. Okay, it can also shift what happens to over to the right, for example, here. So it can shift it to longer times on the transformation diagram. Let me do an example showing you how to read that, okay? So this figure shows a continuous cooling transformation diagram for a 1.13% carbon iron alloy. So label the curves to yield the following microstructures. So here, fine perlite and proeutectoid cementite. So here indicated on the drawing, it shows the transformation in brown here for austenite to the proeutectoid cementite particles. That sticks up above your eutectoid temperature here. So that's austenite to cementite. And then here the second little brown curve is when it starts forming perlite, okay? And then the green curve here is when it finishes that transformation to perlite. And so what I've done is for each one of these problems, I have drawn in my own cooling curve for what would happen with that. So for example, for fine perlite and proeutectoid cementite, what I want is for my cooling curve to cross all the way over that 100% perlite transformation line, okay? So here, it starts off, it's above 800 C, say for example. It crosses this curve going from austenite to cementite. Once it does that, it starts forming those proeutectoid cementite particles. And then here, right here, is where the cooling curve intersects the phase transformation line for beginning the reaction to perlite. And then over here, where the two green curves intersect, that's when it finishes it. Okay, so it's totally finished, and it's got some proeutectoid cementite particles, and then that perlite in there. Okay, next. The blue is indicated for martensite. What's happening for martensite? Well, you don't want your continuous cooling curve to intersect any of these curves if you want it to be all martensite. You don't want those proeutectoid cementite particles to form, and you don't want it to intersect these perlite curves either. So my blue curve kind of starts off and drops very abruptly and steeply down like this, never touching any of those things. And in that case, I would get my martensite in that way. Next, in red, martensite and proeutectoid cementite, but it doesn't want any perlite to form. Well, I've indicated here in red what's happening there. Here, my continuous cooling curve intersects right here, and you can see that's where it starts to form the cementite, the proeutectoid cementite, but it never quite makes it to hitting that onset of the perlite transformation curve. So no perlite is formed, and so I'm just going to get the proeutectoid particles and my martensite. There it is. In the green here, it's coarse perlite and proeutectoid cementite. The only difference between parts A and D here is how long I let the reaction go. You can see the green intersects it way out here, and the black intersects it a little closer in. And as we said, that diffusion takes place over time. So if I allow more time at the higher temperatures, then more diffusion is going to occur. If more diffusion occurs, then I have thicker layers, thicker lamellae, okay? So I just need to let my curve go further out, but still cross this 100% completed line for either of these two things. And the one that takes longer would be the coarse, and the one that takes less time would be the fine perlite structures. So that's the only difference in between those two. Martensite, fine perlite, and proeutectoid cementite. Now that's kind of crazy. I need some of all these things. So that I've indicated here in orange, okay? So it comes down, it intersects my cementite curve here. So it's forming those little proeutectoid cementite particles. Then the reaction begins. Okay, it begins, but it never crosses the green curve, which means that it's not finished. Okay, so the curve never finishes, and instead it gets maybe, say, 60% of the way through, and then the martensite is formed. All right, so that's how to draw those on there. Now let's discuss a little bit what the mechanical properties are and how this works for the percentage of the carbon content, and also what the mechanical properties are for some of these non-equilibrium structures like your bainite, your martensite, your spheroidite, coarse versus fine perlite, and so on and so forth. Okay, so the idea here is that what's going on with your proeutectoid particles. Remember that if you're less than 0.76% by weight of carbon, then your proeutectoid particles are going to be ferrite. And if you're greater than 0.76% by weight carbon, then your proeutectoid particles are going to be cementite. Now, cementite is a much harder and more brittle material than ferrite. Okay, ferrite is softer, more ductile. And so as you cross that line going from 0.7, that 0.76, that eutectoid concentration line, then you're going from something that is much softer and has a lower tensile strength, is more ductile, that's your ferrite composition, over to your cementite composition where you've got your hard, your brittle structure, okay? And it's going to be less ductile. So as you increase the percent by weight of carbon, you go from a lower to a higher tensile strength, and from a higher to a lower ductility. Remember, these things are the inverse of one another. So the more you increase your tensile strength, the more you decrease your ductility, and vice versa. Okay, next, what about the different structures? So you have your fine perlite versus your coarse perlite versus your spheroidite. Okay, so the idea here is, remember this, that whenever you have a grain boundary or a region where you have one material meeting up with another material, those can act as barriers to slip. Okay, when you cross a grain boundary, it acts as a barrier to slip. So what these structures are, this perlite structure, is alternating layers of your ferrite and your cementite. So when you're crossing over from ferrite to cementite, that's a grain boundary basically, okay? And that acts as a barrier to slip. In fine perlite, there's more boundaries, and in coarse perlite, there's fewer boundaries. So coarse perlite is going to be less hard and more ductile than fine perlite because there's more boundaries in fine perlite. Okay. Also, spheroidite has the particles concentrated in these little spheres. Okay, so there's even fewer grain boundaries for that, and so the spheroidite is going to be less hard and more ductile than either of your perlites. Now, on the other hand, your martensite, that's super brittle and super hard, so it's not at all ductile. Okay, so if you compare your values for your perlite to your martensite, you can see that the martensite wouldn't have even fit on those previous plots comparing the fine perlite to the coarse perlite to the spheroidite. It's like a factor of 3 or so larger in terms of its hardness than those. Now sometimes people want a material that's hard but not as brittle as the martensite because the martensite is so brittle that it's almost useless. And so what they do is they heat treat the martensite to form what's called tempered martensite. Tempered martensite is less brittle than regular martensite because the tempering reduces the internal stresses that are caused by that quenching. And what you do to temper something is you heat it up to below that eutectoid temperature and you let it go through some diffusion. Okay, so how hot it is at the tempering kind of dictates what the properties are. And so here we have plotted our tensile strength, our yield strength, and our ductility in these three curves. And then you can see how the tempering works as a function of temperature. So you can see that the tensile strength drops by quite a bit, and the ductility increases by quite a bit when you temper your martensite. And tempering produces these extremely small cementite particles surrounded by your ferrite. So this is going to be sort of spherical looking particles, but the particles are much smaller than that you'd find in spheroidite. So you have more grain boundaries because your little domains of cementite are smaller, so you have more boundaries in there for the same amount of carbon. Okay, so to summarize, possible transformations. If you have that austenite going to a slow cool, then you've got your perlite, okay, and you might have a proeutectoid phase if you're below or above 0.76% by weight carbon. If you go from austenite at a moderate rate of cooling, you get bainite, okay? And then if you cool it really fast, a rapid quench, then you get your martensite, and you can reheat it to get tempered martensite. In terms of the strength, it goes up, spheroidite to perlite to bainite to tempered martensite to martensite, and then your ductility goes the other way with those things. All right, so I hope that helps. Make sure that you read your chapter 10 and come to me with any questions that you might have. I'm happy to help you.